Hello everyone, my name is Chi Liu. I'm a PhD candidate in Rutgers University. I was the instructor of the first Audit Analytics course that offered in last fall. So if you have selected that course, you maybe already have listened to my lectures. I'm very happy to be invited to give this guest lecture in this course, and the topic for this lecture is the association analysis. So in this lecture, I'm going to talk about some basic concept of the association analysis. Also, I'm going to mention some algorithms to do the association analysis. Then I will give you some examples. Also, I'll show you how to apply the association analysis in auditing. And finally, I'm going to show you how to use a tool that we have discussed before called Weka to conduct the association analysis. Okay, first let's see what is association analysis. Association analysis, also called association rule mining, is a technique that in the data mining area, usually the association rule mining is used to find the frequent patterns, associations, correlations, or some rules that will predict the occurrence of an item based on the occurrence of other items in the transaction datasets, relation datasets, and other information repositories. Association analysis is originally used to analyze the transaction data. Also, we could call it market basket data. Because you know that the huge amount of customer purchase data are collected daily at the checkout counters of some stores. So the retailers are interested in analyzing the data to learn about the purchasing behavior of their customers. Such valuable information can be used to support a variety of business-related applications, such as the marketing promotions, the inventory management, and the customer relationship management. So it can also be used to do the marketing and the catalog design. And then it is also applied when we use the other kind of data mining techniques, such as clustering and classification. You can see that here in the slides, there are some examples of the association rules. So the basic form of the rule is like this. When A happens, B is going to happen too. And we always use two parameters to describe the quality of this rule. And we call these two parameters support and confidence. We're going to discuss how to calculate these two parameters in detail in the following slides. For example, this rule shows that if a customer X buys diapers, then he's also likely to buy beers. And this rule with support of 0.5% and confidence is 60%. And the second example of the association rule here listed is that if a person X that has a major of computer science and he takes the course called databases, then he will get the grade A. And for this rule, this support is 1% and its confidence is 75%. Then let's take a look at some of the uses of the association rules. As I said, the original use of association rules is in the market research to analyze the transaction data. It is usually used to analyze purchasing products in X is associated with a purchase in product Y. The rules suggest that a strong relationship exists between the sale of product X and product B, because many customers who buy product X also buy product B. For example, this rule shows that the customer who buys cake mix and milk usually buys X too. And also, this rule shows that products who buy beer will also buy pretzel. And this rule shows that the customers who buy diapers will also buy sleeping pills. So the retailers can use this type of rules to help them identify new opportunities for cross-selling their products to the customers. Association rules is also widely used in the medical research. It is used to analyze experiencing condition X is associated with condition Y. For example, if a patient has virus infection and sinus infection, he is going to have snuffy nose. And if a patient is allergic to something, then it may have irritated nasal passages and stuffy nose. And also, if a patient has fever and sweat, it may lack of sleep, and then he may also have lower resistance. And if a patient has injury and lack of treatment, and he has a chronic pain, then it will be more likely to have swelling. Also, if a patient has swelling, then it will have pain. If it has pain, then he will have swelling, then he will have pain again, etc., etc. So this kind of rules can help the doctor to give their diagnosis. And also it can help the researchers in the medical area to identify the symptoms of some new diseases or something like that. And also discussing the significant associations among some conditions and symptoms can help to determine the causal relationship. But be careful that the rules itself doesn't indicate any causal relationship, because to define the causal relationship, it will need more precise proof. The rule itself only indicates some strong relationship and or correlation between two items. So in order to understand association analysis in more detail, we have to mention the transaction data first. This table illustrates an example of the transaction data. So each row in this table corresponds to a transaction which contains a unique identifier labeled transaction ID and a set of items bought by a given customer. So here we can see that in this table we have the record of 9 transactions, and in each transaction there are some items that included in this transaction. For example, in transaction 1, client buys milk, bread, and eggs. In transaction 2, the client bought bread, sugar, etc., etc. When applying the association rule to the transaction data, we need to first transfer the transaction data to a binary presentation, as shown in this table, where each row corresponds to a transaction and each column corresponds to an item. An item can be treated as a binary flag whose value is 1 if the item is present in the transaction and 0 if the item is not present in the transaction. So we can see that for the transaction 1, it has item A, B, and E, which corresponds to milk, bread, and eggs. And for transaction 2, it includes item B and D, which correspond to the bread and sugar. The reason we need to convert the original transaction data into these binary flags is that this kind of presentation will be more easier for us to do the following calculations. For the parameters we're going to use in association analysis. Besides the item, another concept that we need to understand is called item set. In association analysis, a collection of 0 or more items is termed an item set. If an item set contains k items, it is called a k-item set. For example, the items that included in the transaction 1, milk, bread, and eggs, is a kind of 3-item set. So a transaction can be represented in this format, called by transaction ID and the item set that included in this transaction. After understanding the transaction data, let's start to introduce the first important parameters of the association rule analysis, which is called the support. The support of an item set is an important property, which refers to the number of transactions that contain a particular item set. For example, let's try to calculate the support of the item set ABE in the example dataset. Let's go back to the dataset. We can just try to find how many times that the transaction A, B, and E exist together. It's easily to find that A, B, and E exist twice in this whole dataset, like in transaction 1 and transaction 8. So the support for item set A, B, and E equals to 2. Then let's see another example. Try to find the support of the item set B and C. Let's go back again to see how many times B and C exist together. We can see that in transaction 3, transaction 6, transaction 8, and transaction 9, B and C exist at the same time. So there are 4 items in this dataset, include transaction B and C. So the support of the item set B and C equals to 4. The support count of an item set is connected to a very important concept in the association analysis, which is called the frequent item set. The definition of the frequent item set is that a frequent item set I is one with at least the minimum support count. So the support count of the frequent item set I should be larger or equal to a predefined minimum support count. Okay, it seems not very difficult to understand the support count. Then let's go to the definition of the association rules. An association rule is an implication expression of the form itemset 1 to itemset 2, where in an association rule, itemset 1 and 2 should be disjoint, and itemset 2 should not be empty. It means that if a transaction includes itemset 1, then it will also include itemset 2. So, an example of an association rule that could be generated from the example data is that if a transaction includes itemset A and B, then it also includes itemset E and C. Or if a transaction includes itemset A, then it will also include itemset B and C. Okay, then let's see how to generate association rules from a frequent item set. If we have a question that given a frequent item set A, B, and E, what are the possible association rules that we could generate it from this frequent item set? For example, it is possible that the rule is like if a transaction have A, then it will have B and E also, and if a transaction have A and B, then it will have E also, and if a transaction have A and E, then it will have B, or if a transaction have B, then it will have A and E. If a transaction have B and E, then it can have A also, or even if a transaction have E, then it can also have A and B. So you can see that if we identified a frequent item set, there will be obvious more than one rules that can generate it from this item set. Then it may be even for a small data set, we can find like more than one frequent item set, then we'll have a lot of this kind of association rules. So how can we measure this quality of the association rules? We need to use another parameter to do this measurement. This is the next parameter that we usually use in the association rule. It is called the confidence. According to the previous slides, we know that the support determines how often a rule is applicable to a given dataset, while the confidence determines how frequently items in Y appears in transactions that contain X. So for a given association rule that from I to J, the definition of confidence is that the number of J exists in the transaction divided by the number of these rules, or the number of both I and J exist together in this dataset. You may want to know why we want to use support and confidence to measure the association rules. Support is an important measure because a rule that has very low support may occur simply by chance. And the low support rule is also likely to be uninteresting from a business perspective because it may not be profitable to promote items that customers seldom buy together. For these reasons, support is often used to eliminate uninteresting rules. While confidence, on the other hand, measures the reliability of the inference made by a rule. For a given rule X to Y, the higher the confidence, the more likely it is for Y to be present in transactions that contain X. So confidence also provides an estimate of the conditional probability of Y given X. Therefore, association rules with minimum support and confidence are sometimes called the strong rules. Then let me use an example to show you how to calculate the confidence. So for the same example dataset, if for a given frequent set A, B, and E, what association rules have minimum support equals to 2 and minimal confidence equals to 50%? As you see that in the previous slides, we have several rules that generated from this frequent data set. Then let's test the confidence of these rules one by one. Okay? For example, for the rule from A, B to E, in order to calculate the confidence of this rule, we first calculate the support count of this rule. It is how many times this whole frequent data set appeared together. The A, B, E, like we already counted, it appeared twice in this data set. So it's 2. And then we divide the count of the body of the rule appear alone in the data set, which for this rule is A and B. So we calculate the number of times that A and B appeared together in this data set. You can see that in transaction 1, transaction 4, transaction 8, and transaction 9, A and B appeared together in this data set. So it's equals to 4. Then we use the support count of the rule divided by the support count of the body of the rule, which is the first part. Then we got the result equals to 50%. And then for another rule that from A, E to B, because they are generated from the same frequent data set, so when we count the support of the rule, it's the same, equals to 2. Then we calculate the body, A and E exist together. We can see that in transaction 1 and transaction 8, it exists together. So the confidence of this rule is 100%. Then for the rule, the same for the rule B and E to A, we just need to calculate the count of B and E exist together. It exists in transaction 1 and transaction 8. So it's also its confidence is equals to 100. And then for the rule from E to A and B, we just need to calculate how many times items E exist in this data set. Also exist twice in transaction 1 and transaction 8. So the confidence of this rule is equals to 100. While for the rule from A to B and E, when we calculate the count of A exists in the dataset, we find that A exists in transaction 1, transaction 4, transaction 5, transaction 7, transaction 8, and transaction 9. So A appears 6 times in this dataset. Then you need to use the support of this rule, which equals to 2 divided by 6. So the confidence of this rule is 33%. And for the rule from B to A and E, we find that B exists 7 times in this dataset. So the confidence of this rule is 28%. We can see that for the first 4 rules could achieve this measurement that have minimum support equals to 2 and minimum confidence equals to 50%, while the other 2 rules doesn't satisfy this condition. So using this condition, we could eliminate these 2 rules. We consider them not as strong as the other 4 rules. Now, after our previous discussion, we know that for each association rule, it should have two parameters, minimum support and minimum confidence. And the strong association rules should have support larger or equal to minimum support and confidence larger or equal to minimum confidence. So the association analysis can be described to find all association rules with given minimum support and minimum confidence. Then how can we find these strong association rules? As we discussed before, the first step is to find all frequent item sets. So usually we have two steps in generating the association rules. The first step is to find the frequent item sets. The objective of this step is to find all the item sets that satisfy the minimum support threshold. These item sets are called the frequent item set. Then we start to generate the rules. And the objective of this stage is to extract all the high confidence rules from the frequent item sets found in the previous step. These rules are called strong rules. Like the examples we discussed before, the first step is to find frequent item set, and then next step is to try to find the strong rules that could generate it from this frequent item set. And there is a very important concept in the rule generation, in the association rule analysis. It's called subset property. You may notice this from our previous examples that for all the rules that generated from a given frequent data set, their supports are equal to the support of this frequent item set. So if an item set is frequent, then all the rules generated according to this item set is frequent. Also, we can infer that if an item set is frequent, a sub-item set is also frequent. Like if A, B, E exists two times in this data set, then the subset A or B or E or AB or BE or AE will exist at least twice in this data set. So we call this property the subset property. And this is a very important concept in the association rule generation. Let's see how to generate the frequent item set first. During the frequent item set generation stage, we could use lattice structure like this to enumerate the list of all possible item sets. This figure shows an item set lattice for an item set include A, B, C, D, E, 5 items. In general, a data set that contains k items can potentially generate up to 2.k frequent items. Because k can be very large in many practical applications, the search space for item sets that need to be explored is exponentially large. We usually use a brute force approach for finding frequent item sets, which is to determine the support count for every candidate item set in the lattice structure. To do this, we need to compare each candidate against every transaction, as shown in this figure. So if the candidate is contained in a transaction, its support count will be incremented. For example, the support for bread and milk is incremented 3 times because the item set is contained in transaction 1, transaction 4, and transaction 5. Such an approach can be very time-consuming because it requires to scan the whole dataset a lot of times. Usually, there are several ways to reduce the computational complexity of frequent item set generation. First is to reduce the number of candidate item sets. The Apriori principle that we will discuss in our following slides is an efficient way to eliminate some of the candidate item set without counting their support values. And this is the most widely used algorithm to conduct the association rule analysis. And the second way to reduce the computational complexity of frequent item set is to reduce the number of comparisons. So instead of matching each candidate item set against every transaction, we can reduce the number of comparisons by using more advanced data structures, either to store the candidate item sets or to compress the data set. Because this method requires more advanced knowledge of the database or some other techniques, we're not going to introduce this method in this lecture. And another way to improve the frequent item set generation strategy is to reduce the number of transactions, which could reduce the size of number of transactions as the size of item set increased. This method requires some other more advanced knowledge, so we're going to just mention this here. In the remaining part of this lecture, we will focus on the first way to improve the frequent item set generation strategy. Okay, now I'm going to describe how the support measure helps to reduce the number of candidate item sets explored during the frequent item set generation. In the Apriori algorithm, the use of support for pruning candidate item set is guided by the following principle. If an item set is frequent, then all of its subsets must also be frequent. So this principle means that the support of an item set will never exceed the support of its subsets, and this is known as the anti-monotone property of the support. To illustrate the idea behind the Apriori principle, let's consider the example shown here. For the item set lattice shown in this figure, suppose the item set C, D, and E here is a frequent item set. Clearly, any transaction that contains C, D, E must also contain its subset CD, CE, DE, C, D, and E. As a result, if CDE is frequent, then all subsets of CDE must also be frequent. And conversely, if an item set such as AB is infrequent, then all of its supersets must be infrequent too. As illustrated here, the entire subgroup containing the subset of AB can be pruned immediately once the subset A and B is found to be infrequent. This strategy of trimming the exponential search space based on the support measure is known as support-based pruning. Such a pruning strategy is made possible by a key property of the support measure, namely that the support for an item set never exceeds the support for its subset. This property is also known as the anti-monotone property of the support measure. Actually, this property is the same as the subset property we discussed before, but in the previous slides we just analyze it forward, but now we also illustrate the examples of the backward way. Okay, now let's see specifically how the frequent item set generation in the Apriori algorithm. Apriori is the first association rule mining algorithm that pioneered the use of support-based pruning to systematically control the exponential growth of candidate item sets. This figure provides a high-level illustration of the frequent item set generation part of the a priori algorithm. We assume that the support threshold is 60%, which is equivalent to a minimal support count equals to 3. Initially, every item is considered as a candidate one item set. After counting their supports, the candidate item set Coke and X are discarded because they appear in fewer than 3 transactions. In the next iteration, candidate 2 item sets are generated using only the frequent one item sets, because the a priori principle ensures that all supersets of the infrequent one item sets must be infrequent. Because there are only 4 frequent one item sets: bread, milk, beer, and diaper, the number of candidate 2 item sets generated by the algorithm is 6, like shown here. 2 of these 6 candidates, like beer and bread and beer and milk, are subsequently found to be infrequent after computing their support values. So the remaining 4 candidates are frequent and thus will be used to generate the candidate 3 item sets. Without support-based pruning, there are 20 candidate 3 item sets that can be formed using the 6 items given in this example. While with the a priori principle, we only need to keep candidate 3 item sets whose subsets are frequent, and the only candidate that has this property is bread, milk, and diaper. The effectiveness of the a priori pruning strategy can be shown by counting the number of candidate item sets generated. If every item set is considered, then we will produce 41 candidates. While with a priori principle, this number decreases to 13 candidates, which represents a 68% reduction in the number of candidate item sets, even in this simple example. So this is the frequent item set generation stage in the a priori algorithm. And in practice, the number of frequent item sets produced from a transaction data set can be very large. It is useful to identify a small representation set of item sets from which all other frequent item sets can be derived. There are 2 such representations I'm going to introduce in this lecture in the form of maximal and closed frequent item sets. First, let's describe the maximal frequent item sets. The definition of a maximal frequent item set is that a maximal frequent item set is defined as a frequent item set for which none of its immediate supersets are frequent. To illustrate this concept, consider the item set lattice shown in this figure. The item sets in the lattice are divided into two groups, those that are frequent and those that are infrequent. A frequent item set border, which is presented by the dashed line, is also illustrated in the diagram here. Every item set located above the border is frequent, while those located below the border are infrequent. Among the item sets residing near the border, like AD, ACE, and BCDE, are considered to be maximal frequent item sets because their immediate subsets are infrequent. An item set such as AD is maximal frequent because all of its immediate superset ABD and ACD and ADE are infrequent. In contrast, AC is non-maximal because one of its immediate superset, ACE, is frequent. Maximal frequent item sets effectively provide a compact representation of frequent item sets. In other words, they form the smallest set of item sets from which all frequent item sets can be divided. For example, the frequent item sets shown here in this figure can be divided into two groups. The first group is the frequent item sets that begin with item A that may contain items C, D, or E. This group includes item sets such as A, AC, AD, AE, and ACE. And the second group is that the frequent item sets that begin with items B, C, D, or E. And this group includes item sets such as B, BC, CD, BCDE, etc., etc. So frequent item sets that belong in the first group are subsets of either ACE or AD, while those that belong in the second group are subsets of BCDE. Therefore, the maximal frequent item sets ACE, AD, and BCDE provide a compact representation of the frequent item sets shown in this figure. Maximal frequent item sets provide a valuable representation for datasets that can produce very long frequent item sets, as there are exponentially many frequent item sets in such data. Despite providing a compact representation, maximal frequent item sets do not contain the support information of their subsets. For example, the support of the maximal frequent item sets ACE, AD, and BCDE do not provide any hint about the support of their subsets. So an additional pass over the dataset is therefore needed to determine the support counts of the non-maximal frequent items. In some cases, it might be desirable to have a minimal representation of frequent item sets that preserves the support information. This is the next method we're going to discuss. It's called the closed frequent item sets. The closed frequent item set provide a minimal representation of item sets without losing their support information. And the definition of the closed item set is that an item set X is closed if none of its immediate supersets has exactly the same support count as X. In another way, X is not closed if at least one of its immediate supersets has the same support count as X. For example, in this case, we first calculate the support of each item set. Now here is the support of the 1 item set and 2 item set. And this table lists the support of the 3 item set. We can find that for the 1 item set B, it has 3 immediate supersets AB, BC, and BD. And none of them have exactly the same support count as its, because its support count is 5, and AB's support count is 4, BC's support count is 3, and BD's support count is 4. So we can see B is a closed item set. And this figure also shows an example of the closed item set. To better illustrate the support count of each item set, we have associated each node or each item set in lattice with a list of its corresponding transaction IDs. For example, since the node BC is associated with transaction IDs 1, 2, and 3, its support count is equals to 3. From the transactions given in this diagram, notice that every transaction that contains B also contains C. Consequently, the support for B is identical to B and C. And B should not be considered a closed item set. Similarly, since C occurs in every transaction that contains both A and D, the item set A and D is not closed. On the other hand, BC is a closed item set because it doesn't have the same support count as any of its supersets. Okay, so this is the closed item set. Then what is the closed frequent item set? The definition of a closed frequent item set is that an item set is a closed frequent item set if it is closed and its support is greater than or equal to minimum support requirement. Here in this example, assume that the support threshold is 40%, and BC is a closed frequent item set because its support is 3 divided by 5 equals to 60%. And the rest of the closed frequent item sets, C, D, E, AC, CE, DE, ABC, and ACD. After identifying these closed frequent item sets, we could use them to determine the support counts for the non-closed frequent item sets. For example, consider the frequent item set AD. Because the item set is not closed, its support count must be identical to one of its immediate supersets. So the key is to determine which supersets have exactly the same support count as A and D, because it have 3 supersets ABD, ACD, and ADE. However, any transaction that contains AD, A and D does not have to contain the superset of A and D. For this reason, the support for A and D must be equal to the largest support among its supersets. Since ACD has a larger support than both ABD and ADE, which equals to 40%. So the support for AD must be identical to the support for ACD. So using this methodology, we can compute the support for the non-closed frequent item set. Closed frequent item sets are useful for removing some of the redundant association rules. For example, B is not a closed frequent item set, while BC is closed. The association rule B to DE is therefore redundant because it has the same support on confidence as BC to DE. Such redundant rules are not generated if closed frequent item sets are used for rule generation. Okay, after finishing identifying the frequent item set, let's discuss how to generate association rules from the given or identified frequent item set. For each frequent K item set, usually it could produce up to 2 to the minor K minus 2 association rules, ignoring rules that have empty antecedent or consequence. Association rule can be extracted by partitioning the item set into two non-empty subsets. For example, given a frequent item set L, the item set can be partitioned into F and L minus F, such that L to L minus F could satisfy the confidence threshold. For example, if ABCD is a frequent item set, so there are 14 association rules can be generated from this frequent item set. So specifically, how to efficiently generate rules from the frequent item set? In general, unlike the support measure, the confidence doesn't have any monotone property. For example, the confidence for the rule ABC to D can be larger or smaller than the confidence for the rule AB to D. But the confidence of rules generated from the same item set has an anti-monotony property. For example, for the rules generated from the dataset ABCD, the confidence of the rule ABC to D should be larger or equal to the confidence of the rule AB to CD. And this rule 1 should also be larger or equal to the confidence of the rule A to BCD. Now specifically, I'll show you how the rule generation in Apriori algorithm. The Apriori algorithm uses a level-wise approach for generating association rules, where each level corresponds to the number of items that belong to the rule consequent. Initially, all the high confidence rules that have only one item in the rule consequent are extracted. These rules are then used to generate new candidate rules. For example, if ACD to B, this rule, and ABD to C, these two rules are high confidence rules, then the candidate rule AD to BC is generated by merging the consequence of both rules. This figure shows the lattice structure for the association rules generated from the frequent itemset A, B, C, and D. If any node in the lattice has low confidence, then the entire subgram spanned by the node can be proved immediately. Suppose that the confidence for BCD to A is low. Then all the rules containing items A in its consequent, including CD to AB, BD to AC, BC to AD, and D to ABC, C to ABD, and B to ACD can be discarded. The steps in rule generation in Apriori algorithm is like this. First, generate candidate rules by merging two rules that share the same prefix in the rule consequence. For example, for two rules CD to AB and BD to AC, the merged candidate rule is D to ABC. Then we check whether if its subset AD to BC doesn't have high confidence. If it is, then we could prune this rule. So this rule generation method can make the rule generation step more efficiently. Okay, now let's see an example of the rule generations from item set. This example shows a frequent item set from the golf data. And there are 3 items in this item set. The humidity equals to normal, and windy equals to false, while the play equals to yes. And then from this frequent item set, we could generate 7 potential rules. The first one is if the humidity is normal and it's not windy, then we could play golf. The second rule is if the humidity is normal and we can play golf, then it's not windy. Or we can say if it's not windy and we can play golf, then the humidity is normal, etc. and etc. This shows all the potential rules that could be created from this frequent item set. But if we set the threshold, for example, we set the support equals to 1 and the confidence equals to 100%. And even though this is a small data set, like have only 15 records, then we can still generate 58 association rules that satisfy this condition. And in total, there are 3 rules with support 4, 5 rules with support equals to 3, and 15 rules with support equals to 2. So it's still a large number of rules compared to the small number of records. So even though sometimes we have set the threshold for support and confidence, we still need some other method to additional filter the rules. Okay, now let's talk about how to filter the association rules. As in the example, the association analysis algorithms have the potential to generate a large number of patterns. We can see that we have so many rules even with the small data. And as the size and dimensionality of real commercial datasets can be very large, we could easily end up with thousands or even millions of patterns, many of which might not be interesting. Therefore, we need to find another method to measure the interestedness of the association rules. Lift is one of these widely accepted measures that can be used to evaluate the interestedness of the association rules. It computes the ratio between the rule's confidence and the support of the item set in the rule consequent. Also, we can say that it presents the ratio of confidence to expected confidence. Because lift compares the frequency of a pattern against a baseline frequency computed under the statistical independence assumption, so we can interpret the lift value as if the lift of an association rule I to j larger than 1, then we can say that I and j are positively correlated. While if the lift value of this association rule is smaller than 1, then we can say that I and j are negatively correlated. While if the lift value equals to 1, then I and j are independent. Now I'm going to use an example to show you how to calculate the lift value and why lift value is better than the confidence value. The lift and the confidence value is usually computed based on the frequency counts that tabulated in a contingency table. And this is a contingency table of an example that analyzed the relationship between people who drink tea and coffee. The information given in the table can be used to evaluate the association rule tea to coffee. At the first glance, it may appear that people who drink tea also tend to drink coffee because the rules support, which equals to the item both tea and coffee exist in the dataset, which is 15 out of 100 is equal to 15%. And the confidence of the rule is when the tea exists, the coffee also exists. It's equals to 15 divided by 20. It's 75%. So both these two values are reasonably high. This argument would have been acceptable except that the fraction of people who drink coffee, regardless of whether they drink tea, is 80%, while the fraction of tea drinkers who drink coffee is only 75%. Thus, we can see that a person is a tea drinker actually decreases her probability of being a coffee drinker from 80% to 75%. So the rule tea to coffee is misleading, even though its confidence value is high. So we can see that the confidence value is not sufficient enough to evaluate the quality of the association rules. Then let's calculate the lift of this association rule. According to this definition, we can see that the lift is equals to the confidence of the rule divided by the probability that the coffee exists. So it equals to 0.75 divided by 0.8, which equals to 0.9375. We can see that this rule suggests that there is a slight negative correlation between tea drinkers and coffee drinkers. Therefore, this rule is not very accurate. Okay, for now we have discussed all the basic theories of the association rules. We know that the association rule is used to identify the frequent patterns in the dataset, and its form is from one item set to another item set, which indicate the relationship between these two item sets. And the parameters that are usually used to measure an association rule include the support, confidence, and lift. Okay, let's see how association rule can be used in auditing. As we all know that as an auditor, we need to understand the client's data first. So the auditors can use the association rule to recognize the patterns in client's data. But the auditors are not that interested in the frequent or the normal patterns in the dataset. Controversially, they are more interested in the abnormal or unusual patterns in the dataset because these patterns may indicate the fraud. So using association rule could detect the frequent patterns in the dataset, while according to these frequent patterns, we could also infer some abnormal or unusual patterns in the dataset. So this result could be very helpful for the auditors. For example, we could use the association rule to detect the anomaly combination of items purchased using the company's credit card. Also, if we the auditors to auditor the medical claim data, we could find the unusual combination of diagnosis or the procedures. Also, we could identify the real combination of insurance claims. Okay, then let's take a look at the example of using association rules to analyze the unusual combination of the medical procedures. So the data in this research is the episode data set for the pathology services. There are about 6.8 million records in this data set, and there are more than 100 attributes, so this is a really large data set. In the experiment, several combinations of support and confidence have been tried, and different numbers of rules have been generated. For example, when the minimum confidence is equals to 50% and the minimum support is equals to 1%, then we can get 24 rules. While we change the minimum support to 0.5%, then we can get 64 rules. Then if we change the minimum support to 0.25%, then we can get 135 rules. The example of some interesting rules are here, like if iron studies and thyroid function tests occur together, then there is an 87% chance of full blood examination occurring as well. And this rule was found in the 0.55% of transactions. So for the auditors, if we found a transaction that have both iron studies and thyroid function but didn't have the blood examination, then we may need to flag this record and to do the further investigation because it's not followed the frequent pattern in the dataset. Another example of the rules is that the most commonly ordered combination of tests occurred together in 10.9% of episodes. The rules obtained show that there was a 62.2% chance that if test A was ordered, then test B would also be ordered. Auditors can use this rule to understand the client's data and to evaluate the abnormal. For example, if test B is a very unusual test, but if it appeared together with test A, it is reasonable, then it should not be flagged. Okay, then let me show you how to use the software VECA to conduct the association analysis. Actually, I was planning to use this medical data to show the result to you, but this data is too large and it takes a long time for VECA to run the program. So I chose a sample data set to show you how to use VECA to get the result. Actually, this data is what we have discussed before in the previous slides. It's the weather data. Okay, so first let's take a look at the data. Okay, you can see that this is the data. The data set is very small. It has only 14 records and have 5 attributes. All the attributes are nominal attributes. You can see that in this data set, we didn't convert the data to the binary flag because the Apriori algorithm can only deal with the nominal data. And if we convert this to a 0 and 1 binary flag, then the algorithm will consider those numeric attributes. So we could use true or false or yes or no to indicate the 0 and 1 situation. Okay, then let's go to the VECA. You open the VECA, go to the Explorer. Then first thing is you have to import the data into the VECA. First choose Open File and select the file. It's in the desktop. It's a CSV file called weather. Okay. It shows that in the dataset there are 14 instances and 5 attributes. It's correct. And then when you choose each attribute, it will show the distribution of this attribute. So you can use this as the basic tool to visualize the data. But for the association analysis, first we should choose all the attributes you want to include it in the model. Like here, we want to include all the attributes. Then we choose all. Then we go to Associate to choose algorithms you want to use. Usually here we use a classic Apriori algorithm here. And then when you click this algorithm, you will see some parameters. And if you click more, you can see there are some explanations for this algorithm and for each of these parameters. Usually, we keep most of these parameters in default value, but we could change here the minimum support. If we choose the matrix type as confidence, then here this value means the minimum confidence. And here you can see that we still have several other measures to choose, such as lift. If we choose lift, then this minimum matrix is the value of the minimum lift you want to include it in this model. And also you could choose how many of rules that you want to generalize. Here, let's just go back to choose the classic one, the support and confidence, and keep the number of rules as default, 10 rules. Okay, then you click OK, and then you click Start, so you will see the result. The result shows in order to get the 10 rules, finally the minimum support is equals to 0.25 and the minimum confidence is 0.9, and number of cycles, the iterations, is 15, and the size of the large one item set is 12, and the size of large 2 item sets is 23, etc., etc. And it also lists the rules, and for each rules it lists the support and the confidence. Okay, so you can see that using VECA to do the association analysis is pretty easy. Okay, so let's do a brief review of the contents that covered in this lecture. First, we discuss what is association analysis, and then some basic concepts, and the widely used algorithm for association analysis, which is Apriori, and the steps this algorithm used to generate the association rules. Then we discussed the application of association analysis in auditing, and finally, we show you how to use VECA to conduct the association analysis. So hope you feel that the contents in this lecture is useful for you, and thanks for listening. Bye.